Hello everyone, and welcome to this segment of the course. This is Chapter 2, Module 3, and we're going to be talking about Bitcoin transactions. My name is Patrick Gay. I'm from Ottawa, and I'm Regional Head of a Blockchain Education Network right out there, a huge blockchain enthusiast, and I'm trying to become a blockchain developer. Today we will learn, we'll have a nice little recap of the transaction lifecycle, just so we know where we stand. We're going to talk about what are UTXOs, or unspent transaction outputs. Then we're going to talk about transaction fees and why they would be important. Then transaction scripts, what they are and what are the different skills they can do. And then we're going to finish off with a 1 megabyte block size problem. So the first part of a transaction is the creation or origination of it. It is exactly like writing a check. It can be done offline. It does express your intent to transfer value. So as a check is not actually giving money to someone, giving hard cash. It is an intent to transfer money. The creator does not need to be the one that signs it, basically. The one that signs it needs to have the Bitcoin, needs to be the one owning the Bitcoin. But anyone can actually start a transaction and get it ready for it to be signed. It needs to be in a approved format, of course, and that can be helped with the wallet application that you use. So if it's in the right format and it is signed, then it is broadcast to the network. So when the transaction is broadcasted, the node that receives it will again verify that it's signed and well formatted. It is important to note that the information does not contain any confidential information, credentials, or your private key. What it contains is only and only your signature and the transaction info. Transaction info being who you're gonna send the transaction to, and all the little parameters that that it needs. When it's sent to a node, if it's valid, then that node can add it to its block candidate, and then also at the same time, the node, when it receives that transaction and sees it's valid, it will also propagate that transaction to other nodes in what is called flooding, just to be sure that multiple nodes have that transaction, and then you have more of a chance of that transaction being confirmed into the blockchain. So here's a little neat slide talking about the transaction lifecycle, just a little recap. So Rob wants to send 0.3 BTC to his friend Laura. And you can follow the slide to see all the little steps that you have to take. We're mostly going to be looking at all the steps up to and including here. So all this right here. Now, what are UTXOs and why are they so important? So UTXOs stand for unspent transaction outputs, and they can be thought of as indivisible chunks of Bitcoin currency locked to a specific owner. So let's say I have a total of 1 BTC in my wallet. It is possible that that 1 BTC is represented as a big chunk, a 1 BTC chunk in the network, or it could be multiple different chunks together that total 1 BTC. So a good analogy to that is let's say Bob gives you $20, and that $20 is in your wallet. It's clearly, obviously unspent because it's in your wallet, and it was given to you by Bob. Now, if you think about it, that $20 is Bob's output to you. It's a transaction that he did, and the output was you. Now, if you would like to spend that money, let's say to give $20 to your sister, you will use as input Bob's output, and then output money to your sister, so the $20. So you are basically using the unspent transaction output that you got from Bob to send to your sister as input. I know it's kind of confusing sometimes, but if you think about it more, it makes so much sense. So when you do a Bitcoin transaction, you need to reference a previous unspent transaction as input, like that $20. In most transactions, you will end up with 2 or 3 transaction outputs. So one could be the actual transaction. There doesn't need to be only one person getting the money. You could have a transaction where you send multiple to multiple addresses. There will be the transaction fee. So that one is actually implied. So you don't see it as a transaction output, but it is implied in the transaction and will show up when you look up the transaction. And then the last output would be a change transaction if you record a change. Usually if you have $20 and something costs $15, you're not going to give the $20 and get the service. You will want $5 back because you want that change. References to U2XOs locked to your account are how you know how much Bitcoin you actually have. What is very important to understand is that to spend Bitcoins, you actually spend UTXOs. So to spend Bitcoins, you actually spend UTXOs. Now, there's some very interesting facts about Bitcoin. There's no account balances. The blockchain only logs all the transactions that ever happen on the network. So how our balance is calculated? Well, we can see in the left side here, we have the normal account balance system, where basically, you have an account and you have a balance. You have an account, you have a balance. That's basically how banks work. And then they add a few dollars here, a few dollars there, a few BTCs to an account. So it's just changing zeros and ones. In Bitcoin, you actually, the way to know is how many UTXOs you have. So let's say you have a UTXO that's 1 BTC, one that is 0.1 BTC, then you have 1.1 BTC total. You actually have to calculate how much money you have by adding up all the UTXOs. So to spend money again, and I can't focus on that enough, you have to reference one or more UTXO to cover the total of the transaction. So instead of balances, ownership of funds is verified through links to previous transactions. So here's a very simple diagram of a transaction. You have here the UTXO, what is called mempool. So in the network, there's a memory area, let's say, where you keep all the UTXOs that are unspent. And when someone wants to do a transaction, so let's say Bob wants to send 1 BTC to Alice, he looks at that mempool, looks at the ones that are his. So here we have UTXO 1, 2, and 3, 1, 2, and 4 are his. But he only wants to send 1 BTC, so he's going to look for the closest one. So he sees that 0.3 BTC and 0.9 BTC are pretty close. If you add them up, they become 1.2 Bitcoins. And so he's going to reference both of those in that transaction. Now, as input, he gives his signature. So that's used with a private key to show that it's his and he can unlock those funds. And then gives Alice's public key, the address where it's going to go. In the output, you have basically the transaction Bob towards Alice 1 BTC. And then you need a change output where basically the excess Bitcoin has to come back to Bob. So we want 0.2 BTC to come back to Bob. And then after this transaction has happened, basically it created new UTXOs. So one that is now locked to Alice, and then the change transaction that is still locked to Bob. That goes back to the UTXO pool to be used in the future. So here we have a real life example of a transaction. You can actually find this transaction by looking up at this transaction ID on a block explorer, and you will see it for yourself. So let's imagine that this transaction was from Bob right here on this side to Alice's public key. So right here, let's say this is Alice. We see that Bob transferred 1.239 BTC to Alice, and that the transaction total, everything, the whole Bitcoin that was used in this transaction totals 1.2498 BTC. Remember that any unspent transaction has to be fully spent in a transaction for the whole process to be valid. So here we see that Bob wants to pay 1.239 BTC. Now he has to source enough unspent transaction that he has that are locked to himself to be able to do this. So here we see he sourced 4 of them, 1, 2, 3, and 4, and was able to basically send the 1.239 BTC. Now, because all of those 4 UTXOs are more than the 1.239, he has another transaction that is changed towards for himself. So we can think that this is most likely Bob's public address. So he's sending change back to himself. Also in this transaction that is implied are the transaction fees that are right here. So he's paying fees to the miner for the service that the miner procures. Why are fees important? Very good question. So a fee. To pay for the service that miners provide, and remember, miners verify the transaction. They broadcast it to make sure that a lot of different miners have your transaction, and then they secure the transaction. They make sure that it's added to the blockchain and that it's immutable. Well, you can add a fee, and that's essentially like a tip. Just like a tip for a good service, usually what that means is that if you pay a higher tip, you will usually get a better service. So the higher the fee, the higher the priority you get on your transaction. If you tip the miner well, your confirmation time will be very fast and very simple. If you don't, well, sometimes your confirmation time can take a little while. We can see this actually by going on. So here we have a little diagram, a little neat diagram from Bitcoin Fees 21 delay about Bitcoin transaction and the delay of confirmation. What's important to note here is the wait time for different fees. So if you pay a very small fee, 1 to 20 Satoshi, you could be waiting 35 to 840 minutes for your transaction to be added to a block and to be confirmed into the blockchain. And we can see that as the fees go up, it rapidly declines from 840 minutes to a wait time of 0 to 40 minutes to a wait time essentially of 0 to 30 to be added into a block, a candidate block for the blockchain, and getting that confirmation maybe in the ideal case scenario in 10 minutes. So it's important to actually give fees to the miners because they are doing all the work for you essentially to make sure that your transaction is real, is immutable, and secure. And so a little fee goes a long way for them. So Bitcoin transaction can be more complex than a simple I'm sending you X amount of Bitcoins and that's it. You can actually have scripts involved that add more complexity to it. But scripts are essentially code, so basically instructions that describe how the next person can spend the Bitcoin. They're the ones that lock or unlock the funds inside of UTXOs, and they're the ones also that do multiple different things. So one example is that you can have you can add a script to it where you can have multi-signature transactions, where basically you need 2 people to sign off on a transaction for those funds to be available. You can also have a transaction where you store data on the blockchain called up return, and that essentially just saves data on the blockchain for the fee of sending that transaction to the miner, basically. So with those scripts, you can actually add some different possibilities with a single transaction. Now that we understand how transactions work, I can start getting into the 1 megabyte block size debate in the Bitcoin community. It is a very heated debate about how big the block size should be. As it stands right now, it is only 1 megabyte of data, so that means you can only have 1 megabyte of total transactions inside the block. But as we're going to see, we are exceeding this limit very fast. So here we have a graph of the average block size given by blockchain.info. It's from November 15 to October 16 over here, 2016. And we can see that we started at around 0.5 megabytes, so that was fine, half a megabyte. We had loads of room to put more data in. And there's ebbs and flows, of course, but we are getting towards an average block size of 0.977 megabytes. So we are not far at all from the 1 megabyte limit. And that means that any overflow will just make it so any transaction will take longer to be confirmed and added to a block size. There are pros and cons to the 1 megabyte debate. Some people want to double the size or even quadruple, quintuple the size of the block and then be done with it. And some people just want to keep it as is and say Coda's law, this is it, and the 1 megabyte makes it more secure. So for the pros, a larger block size would mean more transactions per second. Currently, the Bitcoin network can handle about 7 transactions per second, which in the holiday season is actually very slow compared to Visa that is thousands of transactions per second. So that will have to be thought of. Also, there's lower fees per transaction, as you can have more transaction inside a block. The miner will have more chance to make more fees, and so the fees will lower as a direct result. Also, one pro would be that there would be more space to add more diverse information into the blockchain, more information that is there immutable, that is there forever, and it could be interesting to have that. Also, one of the pros is that basically right now no other solution has been agreed upon with the community, and most are not ready. So a lot of people are saying might as well just double the size right now and then be done with it. Now the cons, it would mean that it is a big change of Bitcoin protocol. So that means that you would need to execute a hard fork on the network. So basically that means that you would have potentially, if not everyone reaches consensus, you would have two versions of the blockchain. Also the fees, because they're going to be lowered, they could be too low to incentivize miners to actually secure transactions. Remember that it's very expensive for a miner to run. It's also usually it's a very profitable market right now. A lot of people are saying it's only a patch. It doesn't solve the underlying problem. Also, full nodes need more resources to save data, so more hard drive space. It would mean that is way more expensive. It would also make it cheap to add non-Bitcoin related data. So a lot of people say that storing anything else but transaction in the blockchain is a bad thing, and they just want to see Bitcoin related transactions kept on the blockchain, nothing else. This is a possible damage to decentralization, as you would have only the miners that have access to cheap power, cheap cooling, and they're going to be the ones that have the most say in the network. And so instead of it being decentralized, it's more centralized. And because it's a bigger block, well, it's going to be a slower block propagation on the network. Again, so I just want to talk about two solutions I found interesting for the block size debate. One is called the Segregated Witness BIPs, or Bitcoin Improvement Proposal. So basically, this BIP will actually be implemented in the future, and it very cleverly has the data payload of a transaction. So because it has the data payload of a single transaction, then that means that you can essentially cram double the amount of transaction inside the block. So this is a good hack to be able to keep going with transaction as Bitcoin is scaling up, but it is still not the full answer that we need. One of the possibilities that will alleviate a lot of the transaction on the main chain is to use off-chain payment channels. One of them called the Lightning Network that could be implemented, where basically instead of having all the transaction being done on the blockchain, you would have a little side chain where a transaction happened here and there, and then all the results of those transactions go back to the blockchain as a single transaction, and really removes a lot of the payload of all this data. So those are very interesting proposals. They're in their way to be implemented. At least the segregated witness will be implemented for sure, and the Lightning Network is right now being developed as we speak. So thank you very much. If you have any questions, don't hesitate to ping me on Slack. Also, my LinkedIn is on the beginning of the slide. You can send me any questions you want, and I will try to answer as soon as possible.